There we go. Does anyone have, hello, does anyone have any questions about the project or anything going on before we start the material?
Ooh, I totally do,
Yes.
but it is more of like an explanation question. So I don't know if you want me to wait until the end of the end of the class today.
What's it related to?
It's kind of related to like the third and fourth problems when it's inputting the polynomials into the data
Oh, for the homework?
for the project.
Okay, yeah, yeah, I get, yeah, let's say that to the end.
Okay.
Um, Anyone else? All right, so one good announcement. Um, that last section that we did, I'm looking it over and I'm looking at the amount of time that we've got and everything like that. We're not going to worry about related rates. That's a good thing. I'm sure everyone will agree. I just felt that the material itself is just it's unnecessary. I was talking to another professor about what you guys are going to be doing with this stuff, and we don't need to push you to that level. So that's a good thing. The
So we could basically forget about related rates.
Yeah, I'm not going to give you any assignments. It's not going to appear on your final exam, anything like that. So we'll go up to the global optimization, um, and then like even the applied stuff is just global optimization in word problem form, but definitely, yeah, no related rates. The other thing is I'm looking at the calendar, and we really, by when we finish April, material will be done, and then in May we've got the assignment, the group project, and then the final exam. And so those that time will be allotted towards the group project and also reviewing for the final exam and things like that. So including today's class, we've got really 5 classes. So 4 more after this one in April with material. And the good thing is there really isn't that much material left. So if we get through, when wherever we end up with it, if we have additional time, we can go over things that, if anyone feels like that they want more, practice on and stuff like that, this will be good. So today, we're going to start chapter 4 on on something called integrals. So in Calc 1 and Calc 2, the two major concepts are derivatives and integrals, and both of them come from the concept of limits. And so we're going to start integrals today. In today's lesson, some of these lessons, the time just flies by, have been the normal length of a class as if we were in person. I'm promising you that today's class is going to be shorter, and that we're going to really focus the material in on just a couple concepts. There shouldn't be much by way of calculus terminology or even calculus notation. And then next class, we'll get into the integral notation and how to represent it. But today is just conceptual and trying to connect some things that you've been doing forever and trying to see that calculus is going to allow us to do it even better. And that you've been doing calculus just on a very easy form for a very, very, very long time. All right, I'm going to share my screen over to you guys. It's good. All right, let's do. All right, so that's related rates. All right. So 4.1, determining distance traveled from velocity. This is where we try and make a lot of connections and get calculus connected to something that we've been doing for a while. I'm not going to go through all they have a lot of detail, a lot of reading here. If you're interested in doing that, especially after if you find you're confused maybe with what I'm doing today, read through it. I don't think you're going to be. I think it's actually pretty straightforward, but I think you're going to see things that you didn't necessarily realize. So the first thing that we're going to do is work on this preview activity. And this preview activity really highlights something important. So here's the problem, and I'm going to add something onto this problem because it's missing something. It says, suppose that a person is taking a walk along a straight path, and this person is walking at a constant rate of 3 miles per hour. So imagine you go for a walk, and it actually doesn't really matter that it's on a straight path that much, that we know that. But you're walking at the rate of 3 miles per hour. And imagine that you were to walk for 2 hours at that rate. All right, so you walk 3 miles per hour, you walk for 2 hours. Think to yourself, how many miles did you walk over those 2 hours? I'll give you a second to think about that. right? So if you're 6, over 2 hours, you would have walked 6 miles total if you're walking at the rate of 3 miles per hour. Every hour it goes by, you've walked 3 miles. Well, how do we represent that graphically? Like, how do we think about that in terms of graphs and stuff? Well, one way that we can think about this would be to plot the rate that you're walking at. So what we're going to do, and I'll switch over to Desmos in a second, we're going to plot the fact that you are walking for 2 hours at the rate of 3 miles per hour. And so your x-axis is going to be time, and your y-axis is going to be your velocity, the rate of change that you're walking at. So when we look at that, this is what it looks like. Right? It's just a horizontal straight line because your speed is not changing the entire time. This axis is time, so you can see here you walked 1 hour, and then here's your second hour, and this is the rate that you were walking at the entire time. Think about what formula we use to solve that problem. I mean, this type of problem, you wouldn't use a formula technically, right? I mean, you just do it in your head, but we do have a formula that models this. Nope, right? Distance is equal to rate times time. Very simple, something that you've been using for a very long time. So what does that mean in terms of this picture? Like, is this concept, is the solution, the fact that there's 6 miles that we walked, is it visibly present on this graph? And the answer is, yeah, it is. Let me just draw an extra piece to this graph so I can, so I'm going to draw a line there. So 0 is less than or equal to y, less than or equal to 3. So here we stop. We stop at 2 hours, and all I'm doing is drawing a straight line up to here. What have I created? I've created a rectangle. I'll make it even more obvious. Pay attention to this part because this connection here is essential. So y is equal to 0. My x less than or equal to 2. Okay, these all red. Actually, I'll make these all blue, green. That one's green. I'll make this one green. So only the graph of the original function. Okay. So we've got this rectangle that's formed by these 3 green sides and this red top. Well, what's the area of this rectangle? The area of this rectangle is 2 times 3, which is 6. That's not a coincidence that this is the area of this rectangle is 6 and the distance traveled is 6. They're related. If you have a time and a velocity and you were to graph those, the area underneath that graph is the solution to the distance is equal to RT problem. So the area of the graph underneath the velocity function is the total distance traveled. Now, in something like this, maybe you may not have realized that. I'm pretty sure I had not realized that when I first started studying this stuff. But is that really crazy? I mean, like, is that really something that you need to do? I mean, are you going to go draw rectangles to solve a distance equals RT problem? Totally not. Right? You're not going to do that because D equals RT is easy to solve just by multiplying the numbers together. So why should we even worry about that? Well, because what calculus has shown us and what calculus solved for us is that, prior to calculus, we all had common shapes, and those common shapes we could, actually just lines, we could calculate the slope for. And we couldn't calculate the slopes of curves at a specific point because the slope was always changing. But calculus allows us to calculate the slope at any moment on that graph. Well, it's going to be the same thing for a curve. Imagine that your rate isn't constant and your rate is changing, maybe piecewise or maybe continuously, right? So in terms of piecewise, one example could be, I'm going 3 miles per hour. Now I stop. I now am walking 2 miles per hour. That's piecewise. It's not continuous. There wasn't a moment in time where you were walking 2.5 miles per hour. You were walking 3 miles per hour. Let's say there's a trail in my backyard. So let's say I'm walking down this trail, and for the first hour, I'm walking 3 miles per hour. I stop and take a break for a second. I pause time in my mind because I'm no longer moving, so I'm not gaining any distance. And then after my break, a little bit more tired. Now I'm only going to walk 2 miles per hour for another hour. And so that would be piecewise. Let me do that right here. Actually, so let's just keep with this function. Let's say I did walk for 2 hours at 3 miles per hour. I take a break. I don't advance my position at all. And then I continue on. And this time I'm now going at 2 miles per hour. And that is from hours 2 through for 1 more hour. Okay. And so now, get rid of these. And I want to calculate how far I traveled. Well, you've got 2 rectangles here, 2 different ones. The first one that we saw, which is a 2 by 3 rectangle. We've got a new rectangle, which is 1 by 2, right? From 2 to 3 is 1, and then this is 1 and 2 right here. So this has an area of 2. This has an area of 6. So my total distance traveled is 8. And again, geometry solves this for us. Distance equals RT totally solves this for us. We could just do distance equals RT twice, one for each case. The one where we were walking 3 miles per hour, and then the other one where we were walking at 1 mile per hour. But what if we didn't have something like this? What if we actually had a curve? So what if I wanted to say my velocity was actually increasing for an hour? Let's say I was walking at the rate of x squared, where we're from less than or equal to x less than or equal to 1. So let's say for 1 hour, my velocity was constantly increasing following this. So at time 0, when I first start, I'm not moving at all, so I'm going 0 miles per hour. By the time the hour has elapsed, I'm now walking at the rate of 1 mile per hour. And in between here, I covered all the different rates. Maybe I'm in a car where I can do that, something like that. I mean, these are really slow speeds, obviously. Like here, at some moment, at 0.5, halfway in between 0 and 1. So when was I walking at 1/2 a mile per hour? Well, right around here, in this moment in time. Let's see, a little bit more accurate, right there. Around 0.7 hours, I was walking at the rate of 0.49. A moment later, I'm walking a little bit quicker and a little bit quicker. So my speed is always increasing. My velocity is always increasing over this hour. And then the question would be, how far did I walk? Distance equals RT doesn't help us here. Not obviously, at least it doesn't, right? But there's an answer to this. I mean, that's a problem that could totally happen. Like, it's not we can totally simulate that type of problem. So then how would we go about calculating what that total distance was? And that's where calculus is going to come in. Calculus is going to provide us a standard form that works for the original problem we just started to look at versus this type of problem right here. And it is shockingly easy to be able to do these types of calculations. And once we can do this, it gives us so much more insight into some of the things that we see out there today in terms of even the virus and the models that are coming out there. How do they calculate, the total people infected and stuff like that based off of the rate of infection and things like that through calculus? It's all solved easily for that stuff. So we're going to have to develop that. The one thing I would tell you, and it's a major difference between, let's say, Calc 1 and Calc A. Calc 1, we would develop a limit method of solving this problem. And the way that we would do that is we would draw an infinite amount in the end, but we would draw a lot of rectangles underneath this curve. Because this isn't represented by a rectangle necessarily, but couldn't I draw a rectangle underneath here and say, well, this if I added up all the rectangles that I could draw underneath here, added up the areas of each one of those rectangles, that it would represent this. And if I was to draw an infinite amount of rectangles underneath here and add up the area of each one of those, we would get the exact solution to what the area underneath this curve is, which would also represent the total distance traveled. So in Calc 1, you see how to do that with limits and summation signs and all this other stuff. Things called the right-hand, left-hand method, midpoint method, Riemann sums, things like that. And there's lots of proofs and all this other stuff that go along with that. We're going to jump more to the how do we get to the skipping all the in-betweens and get to the just how do we crunch out these numbers quickly so that we can really use this. So that's the goal, is to be able to figure out how do we calculate the area under a curve, but also knowing in the back of our head what it represents. That in this type of scenario, that it would represent a total distance if what we were doing was mapping time to a velocity. Right? So let's go back to that original problem. Okay. There you are. All right, so let's go back to this original problem. Is there some other type of graph that we could draw that represents this? Because remember, this is the velocity graph. So could we draw a position function, a function that tells us exactly how many miles we have walked after a certain amount of time? And the answer is yeah, there is a function, and that's the purpose of today's lesson. So if you're taking notes at all, the thing that you want to write is what I need to learn today is how do I take a velocity function and find its position function? The way we're going to do this first is by just plotting the things that we definitely know. So there's three things. I worked out this problem ahead of time. And there's three things that I know that you would definitely agree with in terms of its position function. At time 0, I have not moved at all. At time 0, I'm at position 0. All right, so that's the point 0, 0. The next thing about the position function is that I know that after I have walked 1 hour, that, so let me make a note of these. So 0, 0. After I've walked 1 hour, the total distance that I have walked is 3 miles because I'm walking at the rate of 3 miles per hour. So I'm just plotting this. That's all I'm doing. So this is representing specific moments in time along our path, right? So at time 0, I have not traveled a distance at all. So I am at the origin. After I've walked 1 hour, I have traveled 3 miles. So I plot 1, 3. And then the last thing that we definitely know is that after 2 hours, I've walked 6 miles, right? And so I plot those. Now, because our velocity function is a constant, this function, our position function, is going to be linear. It is. I mean, let's pick another point just to see that, because maybe it's just coincidence that all three of these look like they line up. How about a half hour? If I've been walking for a half hour, ask yourself, how long, what's the distance that you traveled? Think about that. All right, so if you're walking 3 miles per hour and you walk for half of those hours, then you walked 1.5 miles, right? So I'm going to put 1.5. Yep. See, these are all lining up in a line. Now the real question is, what's the equation that describes this data? What linear equation would describe this? Well, there's a whole number of ways you can do this. I mean, you've got data points, so you could use the y equals mx plus b and look at the rate. We know what the rate is, it's 3. We could observe it visually, right? For every one, for rise over run type thing. So if I rise, how much do let's go to this blue point because I want to work with the bottom number of 1. If I rise 3 and run 1, right? Rise over run, 3 over 1 is my slope. The speed that I was walking at, that constant speed, is the slope of this position function. And it's at the origin. So that means my y-intercept is 0. So the equation of the position function is y is equal to 3x. See how it connects all those dots together? So I'm going to restrict this to the hours that we're walking, which is 0 through 2. Okay. I'll put a dashed line so that we know that we're looking at the position function and not the velocity function. And so this horizontal line at y is equal to 3 is directly related to this orange dotted line. They are tied together in a very deep, deep relationship. And our question that we have to ask ourselves is, how do we go from this red line all the time, given some red line, whether it's a line or a curve, how do we arrive at its position function? I mean, what I just did is something that seems pretty doable. But what if this wasn't a line? I mean, it wouldn't be as easy. What if it was a curve? See, now, if this was a curve, if that red line was a curve, I wouldn't be able to use y equals mx plus b. Think about why. Think about the reason why we wouldn't be able to use y is equal to mx plus b to represent its position function if its velocity is represented by not a straight line, but by a curve. The reason is, when we came up with the equation for this orange line, we said m is 3 all the time, constantly. And so we were able to use that easily. But if your velocity equation, the red line right there, is a curve, that means your velocity is always changing. And so based off of what time you're at, your velocity is something different. Your slope is different. And so we wouldn't be able to just easily connect these together without some other method of coming up with that equation. We could come up with some of these points for sure. And now that you guys are starting to do some point fitting in Desmos, you have a way of coming up with a pretty easy way of Desmos telling you maybe what the value should be to fit a certain set of points. But there is a numerical way that we should be aware of. And what I'm going to show you, I mean, I'm going to give you a little one term today. But what I'm going to show you is going to be very similar to what we did when we did derivatives. The rules of derivatives, well, we're going to have a whole bunch of rules on integration. Okay, so now the relationship between these two functions, so the term, right, the term that we're going to use here. There's a if, I'm going to put a note in here so that we don't have to go to Word, hopefully. All right, if G and if capital G and lowercase g are functions such that G prime, the derivative of capital G, is actually equal to the lowercase g, right? So if that is true, that you have two functions, a capital G and a lowercase g, and you take the derivative of capital G, whatever it is, if its derivative is equal to lowercase g, then we say G is the, capital G is the antiderivative of lowercase g, the antiderivative. What does Desmos think it should say? Did I spell it wrong? I must have. So that's your one term. I hope I'm not lying to you about that. I hope that's the only term I'm going to give you today. Antiderivative. Right? It's a pretty cool term. Anti-anything, antimatter, all that stuff makes it seem pretty interesting. So when you have two functions that share that relationship, where one function, you take its derivative, you take the derivative of it, and the derivative is the other function that we had, they're antiderivatives of each other. In this case, it's true. The orange and red line here, this orange line is the antiderivative of the red line. The position function is the antiderivative of the velocity function. That's always true. Given a position function and its velocity function, the position function is the antiderivative of its velocity function. You'll be asked to find the antiderivative of functions. That's a major objective. Given some velocity function, or given just any function, whatever it represents, find its antiderivative. So we have to think about what that even means. And the way that we should think about that is, let's go back to when we were just thinking about derivatives. You were given a position function and you were asked to find its derivative. So you would take the position function, take the derivative of that, and you would end up with a velocity function. Well, this kind of sounds like something that's just going backwards, and that's true. If you're given a velocity function, you want to find where it came from. That's all. So it's almost like an inverse, but it's not. These are not inverses, but the process of going backwards and forwards from where you came from, and the ability to do that, because sometimes you can't do that. But when you can, it's a powerful thing because it gives you a lot of information about something. So if you have, in science, it's all about data, and we can collect, depending on what we're studying, sometimes we can only collect certain like growth rates. So if we're collecting a growth rate of something, of a fetus or something like that, right? That's a velocity because it's describing change. But if we want to think about the position of this object that we're talking about, we need to take its antiderivative to describe that original function. So if, something that you'll see in a definite use of calculus in the real world, when you're driving down the road, every once in a blue moon, you'll see like two black cables laying across the road, and you go over it and you just hear a small little thump or click or something like that. Nothing too much. It looks like when you're pulling into a gas station, those things you drive over and it sounds a bell off, right, to tell gas attendant there's someone there. When you're driving over a road, what's happening is the town engineers, they're recording the number of cars, the rate of cars going over specific time periods. They're collecting data is what they're doing. They're collecting raw data now. And they take that raw data and they apply calculus to it. And then they can count the number of cars that go over. They can count the rate of change that they go over per hour. So, one question that would be pertinent, especially in New Jersey, in such a heavily dense populated area, how many cars travel route not let's say the turnpike, how many cars travel the turnpike to New York City every morning between the hours of 7 and 9, something like that. How are they calculating those? They have real numbers. They know how many cars are, and they're not going out there using a camera to capture and count every single car that went by. They're doing math. They're doing calculus on it. And so they'll analyze different things. Sometimes they'll analyze velocities and they'll go backwards from that, or sometimes they'll analyze position and then go towards the velocities and stuff like that. But we can add things up. So just like you can add up the distance, given a rate and amount of time you've been traveling for, we can do that in terms of populations as well, given the rate at which a population is growing at a specific time. We can calculate, how much is that population growing by? Like, what's the new population number if every family is having, 1.5 children, things like that. So let me put this next. Let me put the two equations together. Let's see if we can notice something here. I'm going to put them in order, and I'm going to rename this one to capital G. Because capital G, the 3x, is the antiderivative of lowercase g of x in this case. Look at the two equations. Lowercase g of x is equal to 3. Capital G of x is equal to 3x. And we've determined that they are antiderivatives because when you take the derivative of 3x, you get 3. The derivative of 3x is 3. And that's what we said the velocity was. So that's why these two are antiderivatives. Let's say I'm going to ask you a question to think about. If you have a velocity function, given any velocity function, is its antiderivative unique to itself? So think about that. If g of x is equal to 3, lowercase g of x is equal to 3, could it possibly be that there is more than one antiderivative for this function? Could it have more than one? The answer is yes, it could have more than one. Think about why. Think about what makes two functions antiderivatives of each other. You have to be able to take the derivative of one of them and get the derivative that you have out of it. So are there other functions besides 3x that when you take its derivative, you get only 3 out? Be creative. I mean, I'm going to tell you the answer is yes, there are. Be creative in your mind and see if you can think of another function that isn't the function 3x, that when you take its derivative, you get 3 out. Take a moment to think about that. I think some of you will get that, maybe not everyone, but try to think. It's not a hard, it's not too difficult. If you still don't have it, here's a hint. What can you take the derivative of, and its derivative is 0? Think of something that when you take its derivative, you get 0 out. Hopefully that helped. A constant. I can create another function that when I take its derivative, I get 3 out. 3x plus 1. Right? 3x plus 1. Derivative of 3x plus 1 is 3. So h of x in this case here is also the antiderivative of g of x, of lowercase g of x. But it doesn't represent the problem that we're talking about. Look at why. Because when we started our walk, we were 0 miles from where we were going, from where we were leaving. And if it was 3x plus 1, the solution to our current problem, this tells me that at time 0, I am 1 mile. Or, yeah, I'm 1 mile from my starting position, wherever that was. So 1 mile from some home or something like that. Maybe this 0, 0 represents my house. If 3x plus 1 is the solution to my problem, then that means at time 0, I'm 1 mile from my house already, just starting this process. So even though h of x is a derivative, antiderivative, sorry, of g of x, it isn't the solution to this problem. There are an infinite amount of functions that I can come up with that will have its velocity function as 3. I mean, I can make one n to any number I want, and then that will satisfy that problem. So how do we come up with these values, this 3x plus 1? We don't need to worry about the 1 part yet. I'm going to save that for another day. But how do we get this 3x piece? Thinking backwards, that's how. You have to look at your velocity and say to yourself, what function did this come from? Like, you have to just mentally envision that. You know, if I've got 3 right now, what function could this have possibly have been? And in your mind, you should come up with 3x plus some value, 3x plus some constant number. Okay. Let's take and let's see here if there's see here they give you their definition of antiderivative. All right. So actually, let's just focus on this antiderivative stuff for now. Let's look at a couple of practice problems. Okay, a couple of practice problems. I will open up Word for this, so I can just type them in. Share my screen. Okay. So I'm going to give you a couple examples. Think of see how you do. See if you can figure out where these came from. And I'm gonna give you an easy one. Actually, here's a really easy one. This will be a trig one, which will be this might be shocking that this is easy. What is come on? What is the antiderivative of f of x is equal to cosine of x, right? What is, if f of x is your velocity function, you're traveling, your speed, your velocity can be measured by this cosine of x function at any time. If f of x is equal to that, what is its antiderivative? What function did I have to take the derivative of to get an answer of cosine out? That's what we're asking, right? And we know that sine and cosine bounce back and forth in some way. There's sometimes a sign change, right? But if I was to say, all right, capital F of x is equal to sine of x, the derivative of sine of x is cosine x. So capital F, so sine of x is the antiderivative of cosine of x. Now here's the thing though. Didn't I just show you that there's an infinite amount of solutions? And this is one solution. And we don't have any other information about this problem except that we're looking for the antiderivative. So what we're really looking for is the indefinite. Like we want to be able to come up with a function that could represent any possible outcome, any possible antiderivative that would represent any type of data that they give us. And so what we're going to do is we're going to say plus C for constant, in capital C usually, but you could use the lowercase c. So the antiderivative of f of x is equal to cosine of x. That's capital F of x is equal to sine of x plus c. What's nice about integrals, and probably the only thing nice about it, because integrals I do believe are more challenging than derivatives because you're thinking backwards, is that you can check your work easily. Okay, check your work by taking the derivative of what you believe to be the correct answer. So take the derivative of f of x. Do you get back out what you started with? So when you take the derivative of sine of x, you get cosine. When you take the derivative of c, which is just a number, it's just a constant number. What does a constant number look like graphically? A straight line, like that problem we started with. Its derivative is 0. The derivative of a constant number is just 0 because the slope of a horizontal line is 0. Right? So you can always check your work by you take your proposed solution and take the derivative, and you should get out exactly what you started with. All right, so cosine, let's try another one that's related to that. What is the antiderivative? Try this one at home, of f of x is equal to sine of x. All right, think about that. I'm going to give you a couple seconds to try that one out. What is the antiderivative of sine of x?
Can we say it if we know what it is?
Yeah, go ahead. Go ahead.
Negative cosine of x plus a constant.
Exactly. Negative cosine of x plus c. So it's not just cosine of x, but it's negative cosine. Because remember, when you take the derivative of cosine, just straight up cosine, derivative of positive cosine is negative sine, but we don't have a negative sign here, we have a positive sign. So that means it had to start with a negative already. So the derivative of negative cosine of x is a negative sine of x, which makes it positive. So that would be its antiderivative. That's the one little tricky piece when it comes to sine and cosine and their antiderivatives. It's just accounting for the sign itself. And therefore, if I was to just change the problem to what is the antiderivative of f of x is equal to negative sine of x, that's just going to be positive cosine of x plus c. Pretty, I mean, it at this point it's pretty straightforward. It's just when we get really complicated functions where things can really become challenging. There's a whole bunch of antiderivative integral methods and integration methods and stuff like that. But this process of us thinking backwards, we're actually doing integration right now. We just haven't had a formal definition of it yet. All right, let's try a polynomial. We saw the basic one. We saw when, you know, if f of x is equal to 3, its derivative is 3x plus c. What is the antiderivative of f of x is equal to, let's try a quadratic this time. Let's just do x squared. Actually, no. Let's start with a linear one. Sorry, we haven't done linear yet. What if you're given f of x is equal to x? Think about what its antiderivative is. What function did that just come from? What function did that come from? And one thing that you should think about as well, if its derivative is x, we're using the power rule, right, in some way. And if we were just using the power rule on some function that we're looking for, we would have taken the exponent, put it out in front. We would have subtracted 1 from up in the exponent spot, and we would have changed whatever that number was to now 1, because we're looking at x to the first power. So that means it had to come from x squared, right? The derivative is always 1 degree less than the function it came from. So capital F of x, the antiderivative of lowercase f, has to be in the form of x squared plus c. We're going to have a plus c on everything. But it's definitely not this. And the reason it isn't this is because when I check my work right here, right? So imagine if we thought this was the answer. Check your work. And we would say f prime of x is equal to 2x plus c. Not plus c, sorry, 2x. But it isn't. It's equal to x. It's not equal to 2x. So is that squared wrong? No, it's not. All it means is there's something that's in our in the capital F function that needs to account for the fact that you're going to have a 2 that comes down and then it's got to disappear and become a 1. So think to yourself, what number, I'm going to show you where I'm talking about, right here. What number can I put in front of x squared that when I bring that 2 down and multiply it by it, I end up with a 1? 1/2. So the derivative of 1/2 x squared, 2 times 1/2 is 1. 2 minus 1 is 1. That's now correct. The derivative of 1/2 x squared plus c is just x to the first power. That's where it gets a little tricky, because you got to think about that. You got to be creative in the ways that you come up with this. Try another one. Another polynomial. What is the antiderivative of f of x is equal to, I'm not going to do, let's do this, 2x squared plus 2x squared plus 2x. Now let's just say that. Think about what the antiderivative is of that function. What function did we just take the derivative of to get 2x squared plus 2x? Give you some time to try that out, because you have to think about how these things work. If you're trying to come up with a method in your mind, like how to always do this, we'll eventually have rules, but I gotta tell you, when it comes to polynomials and stuff, we don't follow them. I mean, like, we are following them, but we don't reference them in our mind. It is much easier when it comes to polynomials to just think these things out. So how do you think those out and create a structure for what your answer is going to look like? I know that 2x squared had to come from a cubic equation. I don't know what the number is out in front, but I know it had to come from x to the third. So I'm going to put a placeholder, a, and then I'm going to put my x to the third there. When it comes to the 2x, I know that had to come from a quadratic equation because this is 1 degree, a line is 1 degree less than quadratic. So I'm going to put another placeholder and put x squared. And I know that there's got to be a constant because I got to be able to represent all possible antiderivatives. So my job then, really, because I mean, the exponent part should be really easy to see and understand where that comes from. My job and the hard part is to figure out what A and B are. So, well, we just work it out, honestly. One way could be check your work. Take the derivative of what you've already got right there. So f prime, and then force the numbers. F prime of x is equal to 3ax squared, right? Because I bring the 3 down and I multiply it by the number out front, and then I subtract 1 up there, plus 2bx plus 0, because the derivative of c is 0. So if I'm looking at the structure here, this is x squared, this is x squared, this is x, so that's good. We're good with that. This is 3a and this is 2b, and they need to both be the number 2. Why don't we write that out? Make it into a little algebra equation. All right. 3a needs to be equal to 2. Got to be equal to 2 because of that number in front. I shouldn't have used all 2s. I can see how some of you may get confused by that. All right, so that 2 right there, this 3a needs to equal that 2 right there. So therefore, a is equal to 2/3. I solve for a. And then also 2b, the number in front of x, needs to be equal to this 2 right here. So 2b needs to equal 2 as well in this case. Therefore, b is equal to 1. Right? And so then I just write my final answer as f of x is equal to, so I said a is 2/3, so 2/3 x to the third plus b is 1, so just x squared plus c. Take the derivative of that and make sure that that's true. 3 times 2/3 is 2, x squared, 2x squared. Derivative of x squared is 2x, and there's 2x right there. Derivative of c is 0. Bam, nice and easy. One last problem. I'm going to have you guys try this one out. Now that I've shown you that method, I'll put a couple random numbers out in front and see if you can redo this, and we'll call it a day. What is the antiderivative of f of x is equal to, see if I can make this hard in some way. One over x squared. Of course I can make this difficult. 1 over x squared plus 1/3 x squared plus 1. Yeah, that looks like that's challenging. See if you can figure out the antiderivative. And if that 1 over x squared throws you off and you can't figure that out, that's fine. Move on to the other 2 parts. And you'll just catch up with what you need to do for that. But think about it. See if you can come up with the antiderivative of that. All right, let's work on this. Let's see. Capital F of x equal to. All right, well, I'm going to rewrite lowercase f of x into something that makes it a little bit easier. 1 over x squared, I mean, that's not a polynomial. It's rational. Can I make it look like a polynomial a little bit? Yeah. I can turn that into x to the negative 2. 1 over x squared is just x to the negative 2 power. And we can treat it like all the other ones above it. Plus 1/3 x squared plus 1. All right. So x to the negative 2. It's going to have some number out in front of it. So I'm going to put a. Now it had to come from x to the negative 1. Remember, wouldn't be negative 3. Negative 3 is less than negative 2. It's coming from the degree above it. So that would be x to the negative 1 power plus some value, some constant number in front of x to the third. Because if that's x squared, then its original function had to have an x to the third in it. And then finally, the number 1 needs to have come from x to the first power. So we'll just say c x to the first power plus capital C. That lowercase c is not related to that capital C. Just want to stay in order of ABCs. All right, and then we got to figure out each one of those values. Oh, actually, no. Before we figure out those values, now we're going to take the derivative, right? Take the derivative of the structure that you just created, and then it will present you an algebra problem. So the derivative of capital F is equal to negative a x to the negative 2. Right? I bring the negative 1 out in front, multiply it by the number a, and then subtract 1 from negative 1, and you get negative 2. Plus, the derivative of bx to the third is 3bx squared. And then the derivative of cx is just c. And the derivative of capital C is just 0, right? So 0 can go away. I just want to show you, so you saw that it was there. Okay, so f prime of x, if their derivatives, I mean, if capital F is the antiderivative of lowercase of f, then f prime of x, by definition of antiderivative, is equal to lowercase f of x. So that means negative a has to be equal to, what was our original problem? What number was out in front? 1. Therefore, a is equal to negative 1. We'll check all that in the end to make sure that this is true, but we're just matching things up. Negative a is the number that is in front of 1 over x squared. Here's 1 over x squared. There's the number 1 in front of it. b, 3b, is equal to 1/3. 1/3. Therefore, b is equal to 1/3 divided by 3 is 1/9. And then c, lowercase c, is just by itself, and that is equal to 1. It's already solved. There's nothing there. It's just a 1. So c is equal to 1. So then I'm suggesting that the antiderivative is equal to negative 1 over x squared plus 1/9 x squared plus 1 plus c. Okay. Negative no. Oh, CX, sorry. That's, I knew it looked weird, that 1 plus C. Just 1 plus 1x plus C. Okay, plus 1x plus C. Check your work. Take the derivative of f of x, of this capital F of x. And do we get out the original problem, 1 over x squared plus 1/3 x squared plus 1? Well, this would be x to the negative 2. Negative 2 times negative 1 is positive 2. X to the negative 1. Wait a minute here. Did something wrong, didn't I? Where am I wrong? I'm wrong. Somewhere. I believe I'm wrong.
I got 1 over x for the first part.
Thank you. Thank you. Totally right. Yep. 1 over x. Oh, yeah. I'm referring to the wrong thing, right? It's this. It's this. My structure is right here. Oh, my answer is totally wrong, right? This needs to be a third. That's why I would have realized it here, too. This needs to be a third. Yeah. So using capital F, right? This is capital F here, not the derivative of it. So now when we check this, this will work. Because this is x to the negative 1 power. So then negative 1 times negative is positive. And then you subtract 1 from the negative 1. So that's now negative 2. So positive 1 over x squared. Take the derivative of this. 3 times 1/9 is 1/3 x squared. And then the derivative of 1x is 1. And then the derivative of c is 0. And that is exactly what this is right here. And then that's that. So if you're into puzzles and thinking things like that, this is just one big puzzle where you have to mentally try and come up with this backwards. This is a very cool way of doing it. I don't think your book mentions doing it this way, but I really like it this way. And I think for you guys, this is a very good way because it gives you a definitive way to solve this using math without having to rely too much on the thinking part of it. Provides a structure. So you start with your derivative that you're going to be given, the velocity function, come up with a structure for what its antiderivative would have to be by putting letter constants out in front of it and getting the degrees correct, because the degree will always be 1 degree higher than what its velocity was, and then relating those numbers out in front to the parts of that velocity so that you can figure out what those values should be, and then just rewriting it with those solutions and then checking it one more time to make sure that the derivative of this truly is what you started off with. And that will be your process on how to do this. Okay. I don't believe you're going to see that if you were to look at Khan Academy. I don't believe you're going to see that if you look up anywhere that you're going to see this process described this way. Instead, they're going to give you a rule. And the problem with the rule is if you memorize the rule wrong or on a certain day use the rule incorrectly, your answers are wrong. If you can internalize in your mind the structure and how it should form, then you can come up with this process that will all but guarantee that you're correct. And then as long as you're checking your work by taking the derivative of your final solution, you'll know if you, I mean, you saw me right there. I made a mistake. I noticed it. Took me, I needed some help to figure out where I went wrong. But I realized I definitely had a mistake because I was taking the derivative and it wasn't coming out with what I had originally. So it's just more obvious this way. That's all the information I have for you guys today. Do you have any questions on this, or I think Greg, was it you who had the question on the project, or if anyone's got questions on any of this stuff?
I had a question on the homework.
The homework.
Question 5 on that. I was
Okay.
having some trouble with. I don't think I'm doing it right. I have a Desmos link. That's the graph that I made.
Okay.
But after today's class, I think I'm probably making the y equals p line wrong.
Okay.
But just altogether, I'm having trouble figuring it out. Like I'm getting like a 4th degree polynomial that matches with the graph, and then I can't really like solve for x with that. so I don't know if I'm doing it wrong or what, but me and my group have been trying it over and over and we're having trouble with it.
All right, let me take a look. I'm opening up the homework. My PDF viewer is a little slow right now.
Yeah, I agree. I'm a little stuck with that with the polynomial stuff too.
All right, so and which one? It's question 4 specifically on the homework.
Question 5. 4 I was able to do
5.
all right.
Okay. Let me see. I haven't. I don't think I've worked the problem out. Let me check it out on PDF. Here we go. No, that's the reading.
I feel like question 4 was easier because it gave a function and then it was like the normal routine. You find the derivative and then you set it equal to 0 and then find the critical values and then just work with it from there. But this one was a little harder because it's not like a perfect square when you find the function of it.
Right,
So
right.
like then it was like a 4th degree. Like I tried doing it with like
Should it be a
just
4th? I think you're doing it wrong then. I'm looking at it right now, just at the problem itself. It says
Yeah.
use Desmos to fit a cubic polynomial.
that makes a little more sense then.
It,
All
it,
right.
it shouldn't be crazy hard. Yeah, if it's cubic, I bet you're gonna be able to find it then.
Yeah.
Try it again today and see if making it just into a cubic one, if that will make it will deal with the issue. Let's see, graphically
Okay.
line, and then graphically determine the population. Oh, here's the other thing too. It's saying graphically. I mean, just from reading this, step C says graphically determine the population at which the max.
Oh, you're not supposed to calculate it?
Yeah, I don't think you're supposed. I think you're supposed to just use the graph itself.
Okay. Am I doing the y equals p thing right? I linked the graph that I made in the chat.
Okay, great. Let me see here.
The red line is the y equals p.
I love Desmos. The fact that we can share this stuff so easily. This is
Yeah,
awesome.
it's kind of cool.
Right? Let's see. So y is equal to p. That's the red line. Yeah, right. Because it is supposed to just be on a one-to-one relationship like that.
Yeah, the only problem that I had with it is that it's going up by 10 per thing. So
Okay.
I put the slope as like a slope of 1 because it like fit with the graph graphically, but like
Mm.
the slope is like I mean it doesn't necessarily say that it's per year, but I was assuming that it's like 10,000 per year. And then I'm thinking like it would be like 10x instead of just x, but I just made it like x and it looked like it made more sense, but I don't know.
I've got to work it out to understand even what you're saying because I haven't solved it yet. I can tell you the
Sure.
y equals p is definitely correct. It should be on that like one-to-one type or whatever it is, however many units it changes equally like that. And then you're looking for specifically when the slope of on that curve, right, is also equal to 1.
Yeah.
That p and that tangent line on that curve are parallel to each other. And then that would be the location where you want. Right, that would be the location specifically where you're able to maintain the population.
Yeah.
It doesn't grow or shrink.
All right. Yeah, that makes
Yeah,
sense.
try it out with the cubic. I'll work out the problem so that if you have more, like if you have another question, send it to me. You don't have to if it's still the same exact question, just be like, I'm still stuck there. You don't have to rewrite it again like that.
Okay, gotcha.
Then I'll have something better for you to answer on that. But I think once you change this to a cubic, but then also the fact that you just need to graphically kind of find where that tangent should be parallel, and then
Yeah.
that should be the solution on that.
Should we be sending the Desmos link along with it or just redoing the graph on paper?
You can if you want. Like if you I mean since you use Desmos, I totally would just send the Desmos link. Because why
All right,
draw
sounds
it
good.
out? Yeah.
Okay, thanks.
You're welcome. You're welcome. All right. Anyone want to see something interesting? I was a couple minutes late because I got we stopped to share. This is just crazy. Food is so hard to get, like the food thing is so crazy right now. So we found a company that does bulk food shipping and stuff like that. You have to spend like minimum $250. And so my wife wanted, we have a fire pit in our backyard, and she wanted to be able to do s'mores and stuff like that with the kids. We were having a hard time getting chocolate, but this place sold chocolate. We got chocolate. I didn't realize how much we got. Let me grab it real quick. They said 5 kilograms. And being an American, I have no idea what 1 kilogram is even like in the real world. And this is what 5 kilograms, I should have Googled it, is 11 pounds of chocolate. This, if you can.
Oh, that's awesome.
I don't know if I should be traumatized or elated.
So this is 11 pounds of an enormous amount of chocolate. So I don't think I can't even imagine us finishing this year. So now I got to find a place to put it so it doesn't melt. And we don't have any damn marshmallows either. So for some reason marshmallows are out everywhere. So we can't even.
Yo, time to get an 11-pound marshmallow.
Right? The things that we got today that arrived are just insane. I got 11 pounds of cheese I got because we eat a lot of cheese. That actually doesn't look like this. It is significantly smaller than this. So cheese must be much more dense than chocolate, I guess. I don't know. But if you need any chocolate, let me know so I can sell it by the pound. All right, that's all I have for you. I promise you that I wouldn't take up as much time. Oh, I see there's a couple more. Let me see if there's what's in this chat here. But you're free to go. Let me see if I asked anything. Yeah, so I'll see you guys on Monday. Just work on the project. I will definitely and finish the homework for Friday.
Ooh, before you leave,
Yes.
do you think you can, like, in a way, kind of explain like number 3 in an easier way for me?
For the homework?
Yeah, for the project, the group project.
The project. Let me see. Number 3. Do you have?
It's like applying data.
Okay, let me
Because I'm having a little trouble forming the polynomials for it.
okay. Oh. So the actual fitting of it.
Right.
Did you try? So in Desmos itself? Part of
I
it?
didn't know to open an Excel
Oh, you want
sheet.
to do this in Desmos. So that's the one thing. Make sure there's a couple documents I gave you. The one document that I put on there, it says anything that references Excel should be Desmos.
Right. Okay.
Okay, so you don't need to use Excel at all.
Okay.
You should use the table that's in Desmos. You should put your data in there. And then there's a video, a YouTube video. Watch the YouTube video. Actually, and what I'll do, let me share, screen share you what Greg just sent. It will show you, you'll have to watch the video anyway, but it will explain how easy this is to do in Desmos. I just learned this too. I didn't know how to do this, and it is it's amazing for me. It's just a game changer. I actually sent it to Dr. Amir so that he could see it, because I think it's so much easier. I'm sure Excel's easy too, but I honestly don't know. Here's a set of data, and if you want to point fit this data, what Greg did here was he point fitted it to a degree 4 polynomial.
Right.
And this is what you type in. See what he typed here? This line right here. It's this squiggly line that you've got to use. So if this is your function y sub 1, you can call it y or whatever you want, but it's got to be the column name here. So if this is y sub 1, then you're going to use y sub 1 down here. Squiggly line instead of equals. And then you put these variables, a, x sub 1. The x sub 1 has to be the name of this column. And then you put how, if you want a degree 4 fitting, then you would say to the 4th, and then you'd have to do a 1 for the 3rd, for the square, for the linear, and then for the constant. And what happens is Desmos gives you what A, B, C, and D are going to be. So the polynomial that best fits this in terms of a degree 4 polynomial that fits this data is found by, this is the number that would go in for this a, x to the 4th power, plus this b, x to the 3rd power, plus this c, x squared. So that's the actual function. So only given
Right.
data, Desmos can report back to you what the function should be. I mean, if you delete some of this stuff, it gets weaker. Like it's not as good fitting. If you see his, if I get rid of part of the stuff he's got here, if you're just looking at this, see how it fits? I mean, that data is right there. And then Desmos was able to find the curve that actually connects them all together, and then they tell you it. Now, in terms of degree 4 and greater, Desmos is, what I'm seeing here is that it only gives us 4 variables. So this has got a 5th variable, e. And this is directly related to your project as well, because you have to find it as degree 4. How do you find e? Well, e is just a constant. So that's your y-intercept. So you can find it right down here. E is 2.718. That's crazy, because I think that is the 2.718. Isn't that might be the value of the exponential function e, I think.
And Greg commented that there was supposed to be a plus c at the end of the 2nd degree polynomial at the bottom.
Yeah, so like if we change this problem here to, if I update his stuff, I don't think I'm deleting his work. I don't think so. I could change this to, if we wanted to make it just quadratic, let's say, this would be a x squared, and then I got to make that a sub 1,
Right.
right? And then plus, oh, you know what, you guys, and I bet this will be a question. How do you put the squares in there? Make sure it's shift 6, right? So you're getting that caret symbol.
Yeah.
And the way you do the sub notation is shift, it's the underscore. So when I'm next to B, if I hit shift and then the dash, it goes down. Oh, that should be 1. And then plus C. Oh, I forgot. Oh, this is totally wrong. This needs to be an X. So B, X, X to the 1st power, X sub 1.
Yeah, I was just so lost because my group and I were doing our progress reports,
Yep.
and I wanted to pull my weight for my part of the project and check it out, but
Yeah.
I was just so confused.
Check out the video. I don't know if I linked it directly in the modules or if it's linked within the instructions somewhere along the line. But there's definitely a YouTube video that I watched to learn how to do this that you could watch, but it's only going to show you what I just showed you. So it's
Right.
literally that simple. You put the data, see, but you can see here, like this x squared, it doesn't fit the data as well. Fits it okay, but like here, it doesn't account for this one a little bit above it. So it's not that predictive. But if you made this into a cubic one, you know, it's going to become more and more accurate as you go along. So like if we add that, and then if we say C x sub 1 plus D, there we go. See, and they allow me to use whatever variable I want. See down here, it's calling a capital C since I use capital C there. This one fits it extremely well, right? So this would be good enough. You wouldn't need a degree 4 because your degree 3 totally fits this data as it should be, which means it's representative of it. And it even tells you, you haven't taken statistics, but this R squared factor right here is telling me that it 100% fits the data that I gave it, which is a high level. That's perfect confidence. Sometimes like in your project, in the fetal project, it's probably going to be like maybe a 0.9 or something like that. It isn't going to be perfect, especially since you guys are interpreting the data. But you want to, you know, the more degrees you add
Get it
on,
close as
the
possible.
more accurate it's going to become. And that's what the R squared value here is telling you, is the level of accuracy.
And for the parameters you see there with the like the -0 and stuff,
Yep.
those would be the examples you're talking about, like 10 decimal places.
Yes, exactly.
Okay.
Yeah. And these numbers are exactly just like the numbers that belong in front of these equations here.
Right.
Okay. And now you guys, having seen the stuff that we were just doing, if that the stuff you're plotting is all velocity stuff, right? It's rates of change of the fetal growth. So you can find position functions, and you need to be thinking, and I think probably some of the questions that you're going to be asked on that project are, what does that even mean? Right? Like what does that mean in terms of a fetus and things like that? So, but it really, as someone who's had a couple babies, well, my wife's had a couple babies, but as someone who's been through this process now and things like that, all I can tell you is they look at this stuff hardcore, like it's big time. The doctors are, during the development of the fetus itself, the doctors are always taking measurements, but there's very specific timelines where things get measured. Like specifically 20 weeks, there's a 20-week anatomy check that happens for every single woman that's ever pregnant. You got a 20-week fetus, if your fetus is 20 weeks old, they go in and they count arms, they count legs, they count fingers, they count toes, they count eyes and nose, they measure the shape of they measure the distance of the, let's say the brain and things like that, the length of it. They measure head to toe and stuff like that. Because they've done so much research on fetuses, they can detect abnormalities and issues, because every fetus should be within a certain range of certain things. So this data, and it really, really is interesting. And then even the post-birth, and why this project does go a couple weeks later. The post-birth, when your baby is delivered, I mean, the baby's been sitting in fluid for 9 months. And so just imagine that, like when you're, if you go outside and you haven't been sitting in, fluid for 9 months or something like that, start to dehydrate a bit. And because your body's taking on new processes, so you lose a lot of your weight. You lose, I think, usually a pound. So I think Wyatt was maybe born at 8 pounds. And then, very quickly within a day or something like that, he's then only 7 pounds. They give you rates, like they know that they can measure to see if your child is thriving or not based off of the weight. And one of the goals is maybe within the first month, you need to have, it's within the first week or two, you need to have regained your baby weight. So what you measured at before you were born, within that first week or two, you need to be back at that weight. And I think it's within the first couple months, maybe 3 months or something like that. I don't know off the top of my head, because after the third child, you just start saying whatever. But after a certain amount of weeks, you need to have doubled your baby weight. And if you haven't, to doctors, that's really, really important, because they know that every baby does. And if your baby isn't doing that, then your baby is having an issue. And it is something that needs to then be looked at. So, but that's why, this is useful. It's great application of math, but it really is, it ain't useful in your life yet, hopefully. But it is something that one day, you'll think back to this and be like, oh, I did a project on this, and they really are using the science of this. And the very interesting thing is, and which is what I hate about this project, is the fact that that data is given to you in what is it? It is given to you in weeks. That's a good thing, actually. It's not given to you in months. We never refer to a baby's age in terms of months, because a month is dependent on what month you're talking about. How long is a month? I don't know. I mean, February was 29 days this year. March was 31. So a month is a very bad mathematical unit. It's not really an acceptable mathematical unit. So they always say weeks. So like my baby is, I don't know now, maybe 8, 9 weeks old, something like that. But you say weeks because weeks mean something very specific, 7 days. So days or weeks are the way that we would always measure that. And even in preterm, when the baby's growing inside, they always measure in terms of weeks, and that's what they refer to, because that's why even the whole concept that you carry a baby for 9 months, no, you don't. You don't. You carry the baby for 40 weeks, I think it is. So, because 40 weeks versus 9 months, depending on when you got pregnant, what is 9 months, right? If you got pregnant in January, what are 40 weeks versus 9 months somewhere else along the line? Could have been more than 40 weeks. So things like that, keep in mind. You'll see one day. All right. Any other questions?
Professor, actually, I had a question unrelated. Did you happen to record Monday's lecture this Monday?
I don't know that I did. I'll check. I might have.
Okay.
If I did,
could you please post it?
Yes. Yeah. Now, wait, this month, but I'll post it, but what I'm saying is Monday's lecture, the material that was covered on there, we're not going to go over it anymore.
Oh, any part of it? Because I know that.
Oh, in the beginning, we did some,
like,
right? Yeah, you're right. In the beginning, we did a review, so I could post it. Let me check to make sure I have it. I do believe I have it. I know I didn't post it. Yeah, let me find it and then I'll put it into YouTube and then get it up.
Okay. I mean,
Okay.
I wrote down what's not going to be on. I mean, what you decided the related rates isn't going to be on.
But we did start. We started with that global optimization problem. So that would be, yeah, I'll post it for that.
Okay. Thank you so much, Professor.
You're welcome.
Wait, Professor, did you post the last week lectures on the modules or no? I just want to go over them.
I probably did. I'll let me see what I have. I think I've only posted one. I'm pretty sure I've only posted one. So let me see what I've got and then I'll post those up
Okay, thank you.
there. Okay. Anything else? All right, enjoy this weather. It's hopefully good weather from now on and stay safe. All right.
Stay stress-free.
Yeah, stress free. Hopefully one day we'll get to that.
All right, see you later. Have a good
All right.
day.
You too. Take care.
Thanks. See ya.
Bye.